So the first is evaluating an expression with given different values. So for this first problem, we have b plus a over 4 minus 3. We might find we end up having to use substitution when we're graphing a quadratic, or in other types of problems we'll come across. So for this one, you can see they give you a is equal to 4 and b is equal to 6. So basically all we're doing is just substituting those values in for those variables. So if b is 6, that basically means wherever I saw a b, I'm going to put a 6. Wherever I see an a, I'm going to put a 4. And then we're simply just going to do the order of operations. So you can do this a couple of different ways. One, you can actually just evaluate using the straightforward order of operations. So this would be 6 plus 1 minus 3. And then addition and subtraction, you'd go from left to right. So 7 minus 3, or you would get 4. The other thing you can use is, obviously, in honors, you're going to have to utilize a graphing calculator for graphing quadratics and lots of other things. So you can actually put this in your calculator as long as you're just careful how you're putting it in. And your calculator is going to read it from left to right using the order of operations. So in this case, if I wanted to, if this was like an SAT and I wanted to save time, or I wanted to check my answer, I could actually put that in. You can go ahead and you'd see to get the same answer. Or another feature, if you didn't know, for this calculator, if you do alpha y equals, you can get a fraction, and I can actually type that in and get that same answer, right? So for this problem, I'm showing it by hand, but you can also utilize your graphing calculator. For the second one, it's basically the same type of problem. So this one, we have 3 variables given to us, and they tell us x is 3, y is 1, and z is 4. So I'm going to go ahead and substitute these in. So wherever I see a z, and I'm going to use a parenthesis here, I'm going to put a 4. Wherever I see an x, I'm putting a 3. And this says 3 plus, and then y is 1. So if I want to evaluate it by hand, this would be order of operations. Our parenthesis here would be a 4. This is multiplication. We would have 12. And then 12 minus 4 is 8. We could also utilize our calculator just to get a little more comfortable with it. So if we wanted to put that in, I like to use parentheses when I substitute in, just so I know what I substituted in. You don't have to put it there. You do need the last set of parentheses, though. And you would see we get the very same answer. For the next type of problems we're going to see is talking about simplifying radicals. So when we talk about simplifying radicals, a lot of different ways you can approach this. You can use a factor tree if you like. I'm going to use perfect squares because that ends up being a little bit faster, and at the honors level, you want to get a really good number sense for your perfect squares so you can simplify quickly. And a lot of times these are embedded in problems. So the question might not just be simplify, it's having you use that value to do something with the problem. So what we want to make sure we remember is our perfect squares. So obviously, if we square an integer or a whole number, that's going to give us a perfect square. So I'll make a list here. And I'll just go up to 10, but obviously we could keep going if we wanted to. There we go. And so when we square one of these numbers, that creates our perfect square. So 1, 4, 9, 16, 25, 36, 49, 64, 81, and 100. And again, you could keep going even further if you needed to. So we can do this a couple different ways, and I'll show some ways we can even utilize our calculator again. And so the first one is telling you the square root of 32. So what we're going to do is we are going to use what's called the product property. So what that means is I can break up 32 into two factors where one of those factors is a perfect square. And we usually like to pick the largest. So when I look at this list, we always want to read up the list. So for the square root of 32, I'm going to break it up into two numbers. I could see 100's too big, 81's too big, 64, 36, 25. 32 divided by 25 is a decimal. But it actually works out 16 does work, right? So 32 is divisible by 16. We could break this up into 16 times 2. And the product property tells us that we can break this up into two separate radicals. So what I'm really doing is the square root of 16 times the square root of 2. The square root of 16 I can see is 4, because 4 squared is 16. The square root of 2, I can't simplify that any further. The only perfect square that divides into 2 is 1. And so my answer is 4 radical 2. Now, if you didn't choose your largest perfect square, you would have to go a little bit further. So if I had chosen, instead of 16 and 2, if I had chosen 4 and 8, for example, I would have to go a little bit further because 8 can be broken down into 4 and 2. And you'd get 4 root 2 again. But it takes much longer that way. So finding the largest perfect square is definitely a little bit faster. If we wanted to check our answer, if I look at my calculator, if I check the square root of 32, I get 5.65. If I put in 4 radical 2, I get the same thing. So I know that I did that correctly. There are also ways that you can use your graphing calculator to find your largest perfect square if you wanted to. So I'll maybe show that in one of the later videos, but lots of features you could have. So you definitely want to make sure you have a calculator for the start of the year. For the next one, the square root of 175, it's the same thing. So I'm going to go ahead and find my largest perfect square that divides into 175. So I can see 100 won't work, 81 doesn't work, 64, 36, but 25 does work. So 25 is going to divide into 175. If I divide it in my calculator, I would get, I know that 25 is going to divide in there, and it's going to be 7 times 25. And again, I'm just doing 175 divided by 25. And then if I tried the other ones out, I would see I would get all decimals. The square root of 25 is going to give us 5. The square root of 7, the largest perfect square is 1, so that won't work. So the square root of 175 is equivalent or the same as 5 radical 7. So it's like simplifying a fraction. It's like the grammar rules of math. We need to simplify our radicals. So our final answer would be 5 root 7. For 5 and 6 and 7 and 8, it's basically the same type of problem. We just have variables involved. So if I have a variable, let's say the square root of x to the second, that's the same as x times x. When we do a square root, it's really like having a mini index of 2 here too, right? So we're going to find like if we break it up, it's actually like pulling out a pair. So the square root of x squared would be x. If I was wanting to do this a little faster, we might see that we're really just dividing the exponent by 2, right? Because you're pulling out pairs. So if I had, let's say the square root of x to the 5th, that would be like having 5 x's. And then I would pull out 2 pairs because it's a square root. and you would get x squared root x. But really, it's the same as dividing the exponent by 2. So 5 divided by 2, you would get 2 with a remainder of 1. So the leftovers are in there. So you're going to find that when it's a square root, when it's a positive, well, they're all positive exponents. When it's an even exponent, you're not going to have anything left in the radical. But when it's an odd exponent, you're going to have a remainder. So when we go ahead and solve this out now, when we have variables and values in the same problem, it's kind of the same idea. So I have the square root of 16v squared. That's the same as the square root of 16 times the square root of v squared. You could break it up into separate ones if you like. The square root of 16 just gives us 4. And the square root of v squared, it's like dividing that exponent by 2, right? So 2 divided by 2 is v to the 1, or you pull out one pair. And so our answer would be 4v. For number 6, it's very, very similar. So I have, I'm going to break it up into 2 pieces. So the square root of 196, the square root of x to the 4th. 196, we can try all of our perfect squares in there. And we end up getting, when we divide it out, we end up getting, when I do the square root of 196, we're going to want to try that it actually is a perfect square. We get 14. And then x to the 4th is x to the 2nd. And so 14x squared would be our answer here. For the bottom 2, kind of the same thing. It just so happens they're not perfect squares, but we're going to approach it the same way. So the square root of 18 times the square root of k cubed. 18, the largest perfect square is 9, and then it's 9 and 2. So we get 3 radical 2. And then k to the 3rd, again, if you pull out, there's 3 k's. So 3 divided by 2 means 1 k comes out with a remainder of 1. And then anything on the outside goes together. Anything on the inside goes together. And then for our last problem, same thing. So I have the square root of 48 times the square root of n. Our largest perfect square that goes into 48, even though 4 works, it's actually 16. And then the square root of n. And so now when we put it together, we get 4 root 3n.